Right. Good afternoon, everyone. My name is Jungmin Choi, and I'm a memory system architect from SK hynix. So today, as you can see here, I'm going to talk about some use cases and system benefit of CXL disaggregated memory system. Right. So here is our agenda for this presentation. So I'm going to first talk about the motivation. In particular challenges in today's data center. So why we should focus on CXL disaggregated memory system. And then I will introduce Niagara. That is our CXL disaggregated memory prototype, and then also discuss some use cases that can mitigate the above challenges. And I will end this presentation with an introduction to our future work. All right, so let's first talk about the system issues in these days. So, you know, the volume of data grows exponentially, so we need more cores, and it requires continued increase in memory bandwidth and capacity. But due to some reasons, like some implementation cost and some signal integrity issues, the gap between such a requirement and platform provisioning capability is growing. So we basically need a new approach, and the CXL can address these issues, and CXL-based memory expansion is a decent solution for the issue. And also, the CXL can enable some memory disaggregated system beyond the memory expansion. All right, so from now on, I'm going to talk about some challenges in the data center. So, the first challenge is that the memory utilization of compute cluster varies time to time based on the working set size. But as illustrated left side, the inflexible nature of cloud hardware platform lead to underutilized memory resources, resulting in memory stranding. So, memory is a very costly resource. So the memory stranding due to the platform over-provisioning represent, the significant resource waste. And also there can be a temporary skew in memory usage, causing the data spill, as you shown on the right side. So the storage swap can lead to system performance degradation. All right, so this is a second challenge. So, the distributed computing system can be a powerful solution for large-scale AI applications, such as large language model and also deep learning recommendation model. But it is very important to note that that there can be a data transport overhead between multiple nodes by sharing some data, and also storing that kind of data or shared object in the local memory in each node lead to some data duplication and also increase the memory pressure. So up to this point, we have looked some issues in data center. So now let's explore the solution that can address these challenges. Right, so we propose a disaggregated memory system that can support memory pooling and sharing capability. So, memory pooling can mitigate some memory stranding and data spill issue by sharing disaggregated memory resources between multiple nodes. And I'll explain about it later, but we provide some memory pooling solution that can dynamically allocate or deallocate the disaggregated memory resources for each node. And also, memory sharing can reduce the data transport overhead and also data duplication issues by sharing data or object between the multiple nodes. So this CXL-based memory system offer a significant benefit, but they face a fundamental challenge, the additional latency. So we believe that implementing hotness tracking can help mitigate these issues. But current tracking algorithm like PBS has some notable limitations. So they can track only about half of total memory traffic and also consume lots of CPU cycles. So address these issues, we have developed monitoring logic that can track some hotness of data inside CXL memory. And then this hotness information then can be relayed to the operating system or applications, enabling users to migrate frequently accessed pages from the CXL memory to the local memory. So depending on the workload pattern, we believe that this approach has a potential to enhance the system performance by effectively hiding the latency related to the CXL memory. Okay, so we have built a Niagara hardware-software research platform for CXL disaggregated memory system exploration. Niagara is an FJ-based CXL disaggregated memory prototype, and it is 2U memory appliance. It can connect up to 8 CXL host servers, and it supports up to 4-channel DDR14, and its maximum capacity is 1 terabyte. And it can also support dynamic capacity device described in the CXL spec 3.1 for memory pooling and sharing functionality, and also a hotness monitoring unit described in the CXL spec 3.2 for hotness tracking. So you can see the rack scale system with our Niagara prototype as shown on the right side. So our Niagara provide a comprehensive hardware-software integrated solution for TCD and HMU. So you can see here on the software side for TCD, we have developed TCD handler and memory usage monitor. So I will explain again in the next page, but the memory usage monitor can track some memory usage for each host, then report that data to the orchestrator. So the orchestrator can effectively manage the memory allocation status by requesting memory add or release to the device at optimal time. And for HMU, we provide HMU user library that can configure the HMU inside the CXL memory device. And now we are also in progress of designing the hotness monitoring engine. And that engine will determine when to user to migrate some pages based on the hotness information, while the migration engine will execute the actual page migration from CXL memory to the local memory. And on the hardware side, our solution includes full memory controller for DCD and both DCD and HMU capability, along with full memory manager, similar to the fabric manager. So in summary, our Niagara, or we can provide hardware-software integrated solution to our customers. All right, so let's take a quick look how each feature works. So in DCD mechanism, the memory usage monitor can trace the memory usage on the host servers and report the data to the orchestrator. So if the memory usage reaches either high or low watermark, then the orchestrator can request memory add or release to the pooled memory manager. And then our pooled memory controller actually allocate, deallocate the memory resources for specific host dynamically, and then send that result as an event to that host server. In HMU mechanism, host first should configure the HMU settings to obtain optimal hotness information. So the settings include tracking address range, unit size, epoch length, and hotness threshold. So then our device, our HMU, can monitor the traffic accessing to the tracking address range during the defined epoch length and counting it based on the memory unit size. Then the hotness counter based on the memory unit reaches to the hotness threshold, then our HMU can register that counter value to the hot list, and then host can access the hot list information, then decide whether to initiate the page migration from CXL to the local memory. All right, so this figure illustrates the DCD and HMU-enabled software infrastructure described in previous slide. So in this system, we are evaluating the system performance with DCD and HMU use cases. All right, so now let's look at our some benchmark result. Actually, we collaborated with members to evaluate the system performance with these use cases. So the first use case is memory pooling. So as shown on the left side, the Niagara can dynamically allocate or deallocate the resources for each host. And on the right side, we evaluate the system performance using the CloudSweep benchmark. So notably, spilling 20% of data spilled to the Niagara resulted in performance improvement by up to 2.5 times compared to spilling to NVMe. So we demonstrated that even an FJ-based memory system can effectively mitigate the performance loss. All right. This is a second use case, the memory sharing. So we have modified Ray, an open source based distributed computing framework for AI ML, enabling multiple hosts can share the object within the CXL memory device. And this approach can effectively eliminate the data transfer overhead, resulted in performance improvement up to 5.9 times compared to the native Ray. So these benchmark results prove that our DCD solution can effectively enhance the system performance. Right. We believe that a key use case for HMU is HMSK, heterogeneous memory software development kit. And our other speaker, Hongyu Kim, will cover in more detail in the following sessions. But the HMSK is software solution to support heterogeneous memory system. So in scenarios involving the capacity expansion in the middle of this slide through the CXL memory, the data, the hot and cold page detection and migration are effectively managed using the daemon, the data access monitor. But by applying HMU instead of daemon, we can reduce the profiling overhead and also enhance the tracking accuracy through finer memory granularity in detecting hot and cold pages. So this enhanced page migration decision based on the HMU information can lead to the system performance improvement. All right, so I'd like to invite you to visit our demo booth, the P14. And in the booth, we are showcasing some dynamic memory allocation, deallocation, as well as hotness tracking based on the request from multiple CXL host servers. So in DCD demo, 4 host servers are connected with Niagara, and then if some memory usage for specific host reaches to the high watermark, then the orchestrator requests memory add to the Niagara. So you can see that the allocated CXL memory capacity increases with the memory usage on the right side graph. And our HMU demo illustrate the heat map changes based on the HMU information for each benchmark, so that we can, identify some migration page candidates from CXL to the local memory. All right, so finally, let me briefly outline our future work. And so first, we will evaluate the system performance based on page migration using hot list information. And another key focus will be some disaggregated memory subsystem architecture for AI applications. So we aim to investigate the system benefit by of applying the disaggregated memory to the GPU system for AI workload, such as LLM and DLRM. And we will also explore some value-added functionality of disaggregated memory systems. So the near data processing can be one of our research candidates. And given that pooled memory connected to the multiple hosts, ensuring the system reliability is critical. So developing fault-tolerant memory system will also be an important area of our research. All right, so our works aligned with OCP-CMS, so I'd like to invite you to join us in this effort. And above all, we really would like to do open collaboration with industry partners to enable CXL hardware software ecosystem. All right, so that's all I have for this presentation, and thank you.
Thank you, Jungmin. I'm sorry we're not going to be able to take questions, but it's okay if I offer that you would answer questions either outside or the back of the room?
Yeah.
Okay. Yeah, I've been told that we need to get back on schedule, so Jungmin's available for questions if you have any. Thank you, Jungmin.